Is we could move on. In this context, ISPA, one of the meeting in 2003, decided to bring together all the accelerator community to have the interactions and for the speedy and efficient progress of this accelerator technology. And then it was decided to hold this biennial conference, InPAC, at the DAE centers, which are DRC, RRK, VCC, and IBSC, every alternate 2 years. And this, as you all know, this provides a good forum for the exchange of all the new technologies and all the new accelerator projects. It was also decided that this will be held in addition to all the different whatever workshops we have that is going throughout the year and which is organized by ISPA. Last InPAC was held in Mumbai in March 2023, and so it was decided this year, as per the turn of RRK, to hold this 12th conference of InPAC. This InPAC we have, as Tusharji has mentioned, we have around 300 scientists and engineers, including all the industry delegates and our organizing volunteers. The number is around 450, which is a huge number. But of course, since we started early, so I am seeing the less gathering. So I think we should learn from Dayasji how punctual he is. He is very much in time. All the younger colleagues should learn this to adopt in our future endeavors. Yeah, so going ahead with the description of the InPAC. Now we have around 26 industry participants also, in addition to all the participants from the institution, academic institute, universities. And during this there will be 380 contributing papers which we have received, and after these there will be 26 invited talks and 32 contributory orals, 84 oral posters, and of course 300 posters in 3 poster sessions. Of course, we will have an online talk in the evening. Dr. Pantelio is the renowned physicist in the design of synchrotrons. So he will deliver a talk on the design of the large synchrotrons in the evening, and he will join us online. Earlier he was in Fermilab, just now he has retired from there. And before this he was in France. So in all these lectures and invited talks, all the different machines and all the status of accelerator projects like Indus 1, Indus 2, Cyclotron, Linacs, and all other all the technologies like beam dynamics, magnetic design, superconducting RF system, vacuum technology, and related applications of accelerator. So I think this is a very good opportunity for all of us to have and interact to support our accelerator program of DA. And in 3 PhD presentations, these are from the colleagues who have received PhD last 2 years from the last InPAC. So they will also be there, and ISPA is happy to announce awards for all these posters and best theses. And I would mention here that yesterday Scientific Program Committee Chairman Dr. Vinit Kumar arranged student posters. Of course, it is from these posters only, those students and all the young researchers who showcase. Yesterday in the evening there was one session, and it was very well appreciated, and especially the young researchers got a good opportunity to interact in detail. Of course, in the main poster session they will also be there. So that is a good thing Dr. Vinit Kumar arranged. And I am confident that this InPAC will provide a good opportunity to address all the new challenges and explore the whatever new issues are there in the accelerator-based research and technology. And I will mention here that both the committees, National Organizing Committee and Local Organizing Committee, tried hard, especially Local Organizing Committee, all the chairmen and all the members of the to make this InPAC happen. And I wish that all the out-session participants will be having a comfortable and pleasant stay. And I request all the participants to have the complete advantage of these interactions with all the seniors and of course the juniors. So I wish all the success and thank you.
Thank you, sir, for providing an insightful and comprehensive overview of InPAC 2025. I now request Shri Umesh T. Malshe, Director RRCAT, to address the gathering.
Namaskar. I extend my warm welcome and warm wishes to dignitaries on dais, Homi Baba, Chair Professor at Department of Atomic Energy and former Chairman, Atomic Energy Commission, as well as former Secretary, Department of Atomic Energy, Director, Variable Energy Cyclotron Facility, Dr. Sumit Somji, Additional Director of RRCAT, Shri Tushar Pondambekarji, Director, Proton Accelerator Group of RRCAT, Shri Mahendra Lalji, Chairman Local Organizing Committee of this conference, InPAC 2025, Shri Sanjay Chokseji, and dignitaries of the dais, particularly Director IUSC, Shri Dr. Avinash Pandeji, all distinguished guests, particularly former group directors of RRCAT, senior officers of RRCAT as well as BRC, my colleagues from BRC, RRCAT, from participants from BACC, TIFR, and from academic institutions, industrial partners. A very good morning to all of you. First of all, it is a great pleasure for Rajaramana Center for Advanced Technology and to have a privilege of hosting this DAE-BRNS Indian Particle Accelerator Conference 2025, that is InPAC 2025, and RRCAT family is excited and delighted to welcome everyone over here participating in this conference. Let me first start with thanking Shri K.N. Vyasji for accepting our request to be the chief guest, as well as Dr. Sumit Somji for being the guest of honor for this first Indian Particle Accelerator Conference being organized under aegis of Indian Society for Particle Accelerators. And would like to welcome our guests from abroad, Ms. Hema and Sarwan, to participate in this conference. Came all the way from Formula to participate in this conference. In fact, if you see the logo of many of DA units, you will find the tagline "Atoms in the service of nation." So particle accelerators are not exception to this. Basically, they play a very key role in providing service to the nation. And you all know that RRCAT was established way back in 1984 to diversify and expand the activities of Department of Atomic Energy in the area of accelerators. Therefore, the active R&D programs of RRCAT are well gelling with, aligned pretty well with particularly this particular conference. You all are aware, as it was mentioned by Tushar sir, that RRCAT has designed, commissioned Indus-1, which is operating since 1999, and Indus-2, the second synchrotron radiation source, which is operating since 2005. They are providing synchrotron radiation sources for the researchers across the country. And around 140 research organizations, academic institutes are pursuing research in basic sciences, engineering. They are taking benefit of both these facilities. More than 1,000 experiments are conducted annually at these facilities, which is resulting into around more than 200 publications every year. And in addition to these publications, it is also facilitating development of few of the techniques for the societal benefits as well. Well, Indus 1, Indus 2, these are second and third generation synchrotron radiation sources. Now there is a need for having third, next generation, that is the fourth generation synchrotron radiation source has also been fed. And RRCAT is definitely working in this area to design the fourth generation synchrotron radiation source. In addition to that, RRCAT has a free electron laser facility which is operating in infrared regime and is also available for the research community. Not only for RRCAT research community, but for those from the academic institutions as well as other research institutes, they also can avail this facility. RRCAT has developed a 10 MeV e-LINAC and one of the e-LINAC of 6 megawatt power is operating near the Phool Mandi or Sabji Mandi in Indore. It is being utilized for the medical application, that is for sterilizing the medical devices, and it has reached a landmark of approximately 75 lakhs, more than 75 lakhs it has sterilized medical devices, and is marching gradually towards reaching a milestone of 100 lakhs shortly. So RRCAT has demonstrated, it started with 10 MeV 6 kilowatt particle accelerator, and now it has demonstrated operation of 15 kilowatt e-LINAC as well. And with the help of Atal Incubation Center of RRCAT, we have entered into an incubation agreement with ECI to develop a variant delivering 20 kilowatt, which will be available shortly. So RRCAT team has also initiated the activity of indigenous development to have import substitute of specific systems, particularly the klystron or other systems which are right now being imported, and we expect that these e-LINACs for the societal applications, which will find applications for medical in the medical, to meet such a huge demand in future. Just to give few examples, they have developed a technique to coat the inside surface of a slender and a very narrow surface with a coat of non-evaporator gating, which is a requirement, or rather which is a need of ultra-high vacuum components. Then RRCAT has also developed a zero gap brazing technique for RFQ structures. In addition, in order to enhance the quality factor of superconducting cavities, they have developed a plasma processing technique, and these plasma processed cavities have been delivered and are being tested at Fermilab. So when I said we have delivered to Fermilab, RRCAT is also contributing and continues to contribute towards the international projects. The Indian institutions and Fermilab collaboration is one of the collaboration in which RRCAT is participating along with BRC, VCC and IUAC. We are contributing for the proton axle improvement plan of opportunity to demonstrate the indigenously, or rather the systems developed over here, to carry out the testing at Fermilab and then demonstrate the capability of developing advanced and state-of-the-art system needed for our accelerator program. So that benefit we are definitely getting through this type of collaboration. This indigenization will not be possible without the involvement of Indian industry. And from this perspective, this conference aims a meaningful discussion not only among the designers as well as operators of the particle accelerators, but it also aims to have a discussion with industrial partners, and I believe we have industrial partners as the participants from this conference. So now, before I end, I would like to urge the young generation nominated by their respective organizations to draw the maximum benefit from this Kumbh Mela of particle accelerators. So with that, let me end. But before I end, let me thank you all for participating in this full, productive and inspiring Indian Particle Accelerator Conference 2025. Thank you.
Thank you, sir, for your words of wisdom and encouragement. I request our guest of honor, Dr. Sumit So, Director, VCC, to share a few words with the gathering.
Thank you. Sri K. Dhasa, Sri U.D. Masaji, Sri Mahendra Ladji, Sri Tushar Tuntambekar ji, Sri Sanjay Chokse ji, all the participants, distinguished guests, ladies and gentlemen. First of all, my heartiest greetings to all the participants present here on behalf of EACC. And I would like to thank the organizer for giving me the opportunities to share my experiences with you. As you know, this InPAC is basically a wonderful forum for the researchers or engineers of technologies to discuss the new development and technology with interactions of all the participants and the experts, so that your development is in order or not, you can understand that. So, as you know, nowadays, the inner frontier accelerators are the future, because accelerators are the tools which actually used for industrial purposes, for medical purposes, and of course for basic science research purposes. So all the purposes are being served by the accelerators, from low energy to high energy. So one should concentrate on accelerator, because nowadays you know that in India and in other CAT, this new this 6 GeV synchrotron is in the process, and now other accelerators in India, all cyclotrons, there are 3 cyclotrons in Kolkata, Onuri facilities are coming up. So there are various accelerator programs in DAE, including the 1 GeV proton accelerator for ADSS requirement. So you have a lot of scope. I am talking about the young generations. You have a lot of scopes in this accelerator program. So take this opportunity of this InPAC, a forum for your development, get peer reviewed, and so I feel this InPAC2025, wishing the grand success after this 4-5 days program. So thank you very much. Thank you.
Thank you, sir, for your thoughtful and inspiring words. We are honored to have with us Shri K.N. Vyas, former Chairman, Atomic Energy Commission and former Secretary, Department of Atomic Energy, We express our sincere gratitude to you, sir, for gracing this occasion with your presence today. Though Sri Vyas' eminence in nuclear community is widely recognized, yet, for the benefit of wider audience, I request Ms. Kriti Pathak to give a brief introduction of our chief guest.
नमस्कार, आप सभी का स्वागत है and good morning to all. I sincerely appreciate the chance to introduce today's chief guest, Shri Ken Vyas, at the conference. It is an honor to be involved and I'm grateful for the opportunity. Shri Ken Vyas is an internationally renowned nuclear scientist and Homi Bhabha Chair Professor at the Department of Atomic Energy. He became the chairman to the Atomic Energy Commission and the Secretary to the DA Government of India in 2018, leading the nuclear power program of the country until 2023. He is well known for his outstanding contribution to the design and development of nuclear reactor fuels, thermal hydraulics, and stress analysis of critical reactor core components for various strategic applications in the country. He also played a pivotal role for the design and analysis of test blanket module for ITER, France. Shri Vyas was chairing several committees and commissions of national importance throughout his professional career and continues to be actively involved in India's nuclear power program to meet growing energy needs and net zero target of the year. He is a fellow of the Indian National Academy of Engineers and received several prestigious awards including the Homi Bhabha Science and Technology Award, Indian Nuclear Society Outstanding Service Award, and DA Excellence Awards in Science, Engineering and Technology. Sir, I now invite you to enlighten the audience with your words of wisdom.
Really grateful for the kind words. I hope I deserve whatever is spoken about me. Friends and colleagues on the dais, Dr. Sumit Som, Director VECC and today's guest of honor, Mr. Marshe, Director RRCAT, Mr. Puntambekar, Additional Director RRCAT, Mr. Lard, Group Director of Proton Accelerator Group, Mr. Chokse, Convener of the Local Organizing Committee, Director IUSC, Dr. Pandey, my senior from 17th batch, Dr. Singh sir, who has played a key role in commissioning of Indus 1, 2 and all the work which is done at RRCAT, colleagues from Fermilab, all colleagues from DAE fraternity, students from university. A very good morning to you all. Let me start with a short interaction I had with Dr. Gianotti when I had a chance occasion to meet her about 6 years back. She invited me to CERN and she said that please have a visit of a couple of days to CERN. So at that time I had told her that I neither understand physics nor I understand electronics. So I don't know any visit to CERN will be of any use to me or not. Finally the visit did not take place and I still sort of acknowledge that whatever I spoke about 5.5, 6 years back is still valid. I neither understand physics nor I understand electronics, which is a key part of all the particle accelerators. I'm just an average mechanical engineer trying to sort of make some meaning out of whatever I have learned. So we can understand the importance of particle accelerators from the fact that Professor Meghnad Saha had the audacity, even before independence, to import a cyclotron. Unfortunately, it did not take place because of that Second World War, and I mean, all of you who are in the particle accelerator field, you know very well some of the systems, etc., sort of sunk during the traveling. I mean, the idea was to get from the cyclotron from Professor Lawrence himself, but it did not happen. But finally, yes, in Calcutta, we have 3 cyclotrons, and as Professor Vikas Sinha says, it is a city of cyclotrons, and it is so very true. But we can understand for high energy physics, both Professor Meghnad Saha and Dr. Homi Bhabha, who thought that in TIFR we should have accelerators, and then that Cockcroft-Walton accelerator was established. So we all understand for studies on high energy physics, particle accelerators, it could be a linear accelerator or it could be a cyclotron. They are playing a very important role. My first exposure to this particular technology sort of came in the year of 2016 when I became director of Power Atomic Research Center, and I was briefed about LEPA from Dr. Krishna Gopal, from Mr. Sanjay Malhotra, from Dr. Gopal Joshi. So they all briefed me. I must admit I really did not understand much, and I realized that I will not be able to make any significant contribution by giving them technical knowledge. I tried to support them to whatever extent possible. Only I could learn was that RFQ doesn't stand for request for quotation, it stands for radio frequency quadrupole. So these are some of the things which I still happen to I happen to still remember. I still do not know exactly the complexities of making this particular aspect. I had later on a chance to visit RRCAT, where Dr. P.D. Gupta explained me the working of synchrotron. He explained me at that time 3 electron laser was also under design stage and initial sort of development stage. And I find this is extremely, I would say, extremely complex set of technologies where when you do bunching of various particles, you are talking in terms of a very small time magnitude, so it is extremely good quality of stable electronics, so that whatever that you the part of say manipulation using radio frequencies.
हम तो इंटरनेट चेक कर लीजिए, इंटरनेट चल रहा है ना, वो चेक कर लीजिए.
Now, what there is a my predecessor also he said about young people. So I have become too old. So there is a bit of wish list only which I can have from young people. If I can speak coherently for 10 minutes, that itself is an achievement nowadays. So nowadays I speak also sometimes randomly. So I am coming to my wish list. Number 1 is when it comes to scientific community, the particle accelerators, they are being used. We are in a position to get a very good useful output out of that. We are able to understand the basic science. But today morning only I was discussing with Dr. Pandey some industrial uses are not sort of equally in vogue. Like I have been it has been just indicated by Mr. Marshall that there are about world over there are about 30,000 or so particle accelerators. Majority of them are in the field in industrial fields. It could be radiation processing, some little less expensive, and we are able to deploy these devices. I would say my experience of working at with the LEPA colleagues is we have picked up some very finer points with the help of Fermilab collaboration. In any technology, there are some finer nuances of technology which one has to learn hard way, and we are thankful for this IIFC collaboration that we have been able to interact with the specialists from USA as well as some of the specialists in the world also, and we have been able to pick up. So we have reached a reasonable one of my wish list. Second wish list is something related to the third synchrotron that we are talking of. The former, yesterday only I had mentioned this particular aspect. The previous principal scientific advisor to the government of India, he had put in, Professor Vijay Raghavan sir had put in tremendous amount of effort in sort of trying to push that particular project. The present PSSR is also this particular project in a reasonably sort of assured time frame. So, fine, let me just tell one thing about that industrial application. From BRC side, BDDG was very keen on having some industrial application of the electron, that is electron beam machine, and from RRCAT side also the industrial application was being attempted. What I feel is for industrial use, the machine should have adequate ruggedity. I'm so sorry, ruggedness, and there is a when relatively the persons are not familiar with the operations, certain mistakes may take place. So certain amount of fault tolerance, the power supply may not be so stable, so this should be there. So I feel if a few accelerators are deployed in the field outside, we will have better confidence in whatever machines that we are building. BRC machine, despite their best effort, could not be deployed. It was meant for, I would say, treating the wastewater from the tanneries, which is extremely dirty. But then the trials were taken place, but it could not be field deployed. But fortunately, the RRCAT machine, it has been deployed with industry at Bangalore. And let us hope that we get good feedback from there, so that we have a machine which is of better quality. So I think with this I would like to end. I wish the best of deliberations. When I went through the list of the I would say invited talks and the titles of the various posters and oral poster presentations, I found that the field is very wide in form of vacuum technologies, in form of magnetics, in form of RF technologies and so on. So I hope you are able to make best use of it. I also wish that you make good friendship here, so that it can result into future collaborations, because there are we have I would say the specialization in very specific areas. When we collaborate, it sort of makes it little better to finally make a product which can be used by the experimenters as well as the industry. Thank you very much, and Jai.
Thank you, sir, for your insightful and inspiring words. Now, I request the dignitaries on the dais to kindly be seated in the audience. Our guest of honor, Dr. Sumit Soam, is well known in particle accelerator community and needs no introduction. However, for the benefit of the wider audience, I would like to give his brief introduction. Dr. Sumit Soam, a distinguished scientist, is presently Director of Renewable Energy Cyclotron Center at Kolkata. He is an Electronics and Telecommunication Engineering graduate from Indian Institute of Engineering Science and Technology, Shivpur. He joined BCC in 1988 after graduating from 31st batch of VRC Training School. He has worked in several areas of particle accelerators, especially on RF technology. He has received several technical achievement awards of DAE like Homi Bhabha Science and Technology Award, Science and Technology Excellence Award, and Group Achievement Award. With this brief introduction, sir, I now invite you to present the keynote address.
Thank you. Thank you very much. So, I will be talking about cyclotron technologies and its applications in basic science, research, and healthcare. So, this is the main campus of ACC. It is in the area of Kolkata near airport. So now, first of all, I will tell about some brief history of establishment of cyclotrons in Kolkata. As you know, the nucleus was discovered by Lord Rutherford in the beginning of 20th century by bombarding helium ions on gold form. Then, as Vassar was already mentioned, Professor Meghnad Saha, the iconic astrophysicist and famous for his discovery of Saha equation, Saha ionization equation, first realized that in India, the accelerator like cyclotron was needed to study the nucleus. On 11th of January 1950, Nobel laureate Irene Joliet Curie, who actually got the Nobel Prize in 1935 and who was the daughter of Madame Curie, she inaugurated Institute of Nuclear Physics, which was established by Professor Meghnad Saha in Calcutta. That time it was Calcutta, not Kolkata. Dr. B.D. Nath-Chaudhuri, the student of Professor Saha, was already working with Professor Lawrence, Theo Lawrence, who actually invented cyclotron at Berkeley, University of California, Berkeley, and he was conferred with Nobel Prize in 1939 for the discovery of this cyclotron. And with the help of Professor Lawrence, Dr. B.D. Nath-Chaudhuri managed to get the components and install the first small cyclotron. Actually, what Vassar was already told, most of the components were actually drowned during the World War II. And some components he got and some components were made in Kolkata that time in Raja Science College under Calcutta University. And that worked well. That is the basic proof of principle of cyclotron. And that is still there in a museum. And in 1960, Dr. Raja Ramanna, member of SINP Council, Saha Institute of Nuclear Physics Council, that Institute of Nuclear Physics was renamed as Saha Institute of Nuclear Physics, and he was the member of the council and head of the physics group of BRC, felt the need for a large-scale cyclotron to be built indigenously. Now, Dr. Raja Ramanna managed to persuade Dr. Homi Bhabha and then Professor Dr. Vikram Sarabhai to approve the K130 cyclotron project, which is a replica of Berkeley 130 cyclotron. Finally, the first large-scale indigenously built Day-1 cyclotron was commissioned on 16 June 1977 at DECC, and subsequently the 16th June every year is celebrated as the foundation day of it. And after that, K500 superconducting cyclotron similar to that of Texas A&M University and MSU, Michigan State University cyclotron was indigenously developed and commissioned at DCC and now delivering high energy heavy ion beam to the users on round the clock basis. Then a 30 MeV medical cyclotron, which is basically a IBA cyclotron, 30 MeV, has been installed and commissioned at another campus of DCC, and which commercial production and supply of radiopharmaceuticals is since 2012. Currently, the development of indigenous 18 MeV medical cyclotron is in progress at DCC in collaboration with BRC. Now, as you know, DCC is one of the R&D units under the Department of Atomic Energy and primarily engaged in the research in basic sciences since its inception in 1969, and also the development of accelerators and related technologies. So major activities of VCC actually broadly it is basic sciences, for example, experimental research in low and high nuclear physics using accelerators and theoretical nuclear physics, accelerator-based applied research in the field of material science and radiation damage studies, societal applications like medical cyclotron for isotope production, indigenous accelerator development, and R&D and advanced accelerator, and then technical development on RF detectors, data acquisition, instrumentation, power electronics, mechanical, cryogenics, computer, IT services, etc., etc. So now, as you know, VCC is having 3 cyclotrons. This is the K130 cyclotron, this is the K500 superconducting cyclotron, this is the 30 MeV medical cyclotron. Now, for the sake of completeness, this is the cyclotron, and this beam is actually, in cyclotron there is a magnet, there is a RF, and magnet is used for bending the beam, RF for accelerating the beam, and there are taking the beam out, they need deflector, then ion source, etc. are required, and so this is the basic fundamentals of cyclotron, where the accelerating cavities are there, where the RF voltage is produced for acceleration. And there are various components of cyclotrons. For example, ion source, injection beam lines, and then main magnet, either it is normal conducting or superconducting, radio frequency system, which consisted of high power RF and low power RF, LLRF and high power RF, vacuum system, control system, beam extraction for example, deflector based or stripper based, extraction beam line, experimental facilities, etc. I might have these some components also. So, first I have told that ion source is required for the cyclotron or any accelerator to operate. So VCC is the place where the first indigenous ECR ion source was developed in 1993. And after that we have developed many ECR ion sources. First was the 6.4 gigahertz ECR ion source, and then we have made for RI requirement 2.4 gigahertz ECR sources, 14.45 gigahertz ECR sources are used for K130 cyclotron, and another one for this superconducting cyclotron. So this is the picture of the ECR based ECR ion source, which is being used for right now. The first ECR source is being used for material science research, because this 6.4 gigahertz is no longer used with the cyclotron. 14.45 gigahertz is being used with the cyclotron. This is the 14.45 gigahertz ECR source, which is actually connected to the one to the K130 and another to the K500 cyclotron. So these are the this is the cyclotron, and now there are ECR2, ECR3. So here one cyclotron is connected to ECR2, another is ECR3. So this is the K130 cyclotron, which is the workhorse, because because as I understand, lot of nuclear physicists all over India, somewhere or other, is connected. They have done their experiments with this cyclotron, and lots of PhDs have been come out doing experiments with this cyclotron. And this cyclotron has these 3 beam lines for nuclear physics and irradiation studies, and there is another beam line which is 159, almost 160 degree, this BIST line, and it is going to RIP facility as a primary beam to the RIP facility. So this cyclotron, actually in 1960s, the industrial infrastructure of the country was not adequate to meet the requirement for a large scale cyclotron. Despite the situation, as mentioned above, 200-ton magnet for this K130 cyclotron was successfully built by the Heavy Engineering Corporation last year. So they had a lot of capability to make the magnet high, this large scale magnet, and the radio frequency cavity. This is the radio frequency, the peak cavity. It is because the frequency is 5.5 megahertz, the old cyclotron frequencies, lowest frequency is 5.5 megahertz and the highest is 16.5. So the cavity dimension is a very large one, and that mainly shipbuilders and engineers that time in 60s, in 60s or 70s like that. So this is the ICR source of this 14.45 gigahertz, and it is being used for K130 cyclotron, and another one is for K500 cyclotron. These are the various beam lines. This is the highway, and then it is going down to the cyclotron side through the vertical injection line. And from these ECR ion sources, we have also developed solid ions like sulfur 10 ion and accelerated using the cyclotron. So currently all these beams, like from K130 cyclotron, these beams are being used by the users. Say alpha, proton, sulfur, nitrogen, 5+, neon, oxygen, and you see alpha beam is only available in VCs. This is the K500 superconducting cyclotron. Here the magnet is a superconducting one, and this is magnetic field is up to 5 Tesla. So this is the superconducting cyclotron. This is a very compact and a very complicated machine. And then inside this there is this magnet of 5 Tesla, and inside the cryostat at a liquid helium temperature, and then the beam is coming out, and through this beam line it is going to the cave. And so this is the beam injection from 14.45, I told one another 14.45 gigahertz PCR is there. So this is the this is the beam is from this ECR ion source. Beam is coming to the main magnet, main cyclotron, and then after acceleration it is going out through this beam lines. So if you see, this is the, then it is coming out. So this is the, if you see the inside cross section of the cyclotron, K130 cyclotron, this is the beam, and this beam is after accelerating, it is coming out through the deflector system. We have a 2 deflector system, it is coming out from the machine, and then it goes to the through the external beam line, goes to the cave. So we have a plan for 3 beam lines. Currently we have 1 beam line, and we have already any time we get the time, we will install the other 2 beam lines. So this is the first beam line which is right now operating and giving beam to the users. We have another beam lines to be installed. So this is second one, and the third one is for gamma spectroscope. So if you see, these are the various components of the K500 beam lines, and where the beam viewers etc. are there, you can see the beam spot here. So this is the beam spot in this. So just beam is going there and then it is going to the target and the experiments are going. Now I am coming to the extracted beams and delivered to the users. These are the beams already extracted and being utilized by the users round the clock, and highest beam of the order of around 30 MeV per nucleon, which is about this nitrogen 5 plus beam, 30 MeV, almost 30 MeV per nucleon, and then so 18 MeV to 30 MeV. All these beams, if you see neon 6 plus, oxygen 5 plus, nitrogen 4 plus, 5 plus, etc. All these beams are already being used by the users currently. Right now, at this moment, this 289 MeV beam is being used by the users. So, in superconducting cyclotron, as I have already mentioned, the cyclotron is basically the 3D system. 3 cavities are there, and these 3 cavities, the power is being made from the amplifiers. 3 amplifiers to the cavities, and this is the main magnet is this, as you know, K bending is 500, K focusing is 160, and average magnetic field is 5 Tesla. The superconducting, the magnet iron part is total 100 pound, and then 12.5 ton cryostat, the weight of the cryostat, and the frequency is 9 MHz to 27 MHz operating frequency, and maximum key voltage is of the order of 80 kV. It operates from say 50 kV to 80 kV depending on the user's requirement, whatever energy they want or like that. So this is the control room of the, this is the experimental cave, this first cave, this is the scattering chamber. And here you see this is the magnet structure, this is inside, I am talking about the inside the main machine. This is the magnet structure, this valley, and in the valley there are Ds installed, the RF cavities, and this is the pole structure. So this is the median plane, and these are the pole radius height is this, and if you see these are during the assembly, all these components, this is this fabrication of magnet of the superconducting cyclotron. The iron part of the magnet is also similar to the K130 cyclotron. This was also done at Heavy Engineering Corporation also. So they had a lot of facilities. Right now there is a problem in there, and this is the cryostat while this assembly was going on, fabrication and assembly was going on. And here I can tell you that the coil is a superconducting coil of niobium titanium multi-filament composite. It has a critical current of almost 1000 ampere at 5.5 Tesla and 4.2 K, consisting of 500 filaments of 540 micron diameter embedded in copper matrix of 1:20. That is 20 part is copper, 1 part is superconductor, and that means 1 part is superconductor and most of the parts are copper. Why? Because it is a very cryostable magnet. The magnet started operating since 2000, and till today the magnet has never quenched in 25 years. So this is a cryostable magnet. And there are 2 independently powered coils, and namely alpha and beta coil. So there we have to choose the coil current so that we get the right magnetic field. And this is during the assembly. You see there are multi-layer insulations, and then liquid nitrogen seal. So there are also one more thing is that there are lots of penetration through the cryostat, because you have to have the diagnostic elements to be connected. So almost 20 radial penetrations are there. So and then cryogenic lines and power PQs are connected from the top. And this is the during the assembly in the magnet. So when multi-layer insulation is already in place. And this is the there are in magnet there are main magnet there are 13 trim coils, and each trim coil total up down total is 78 trim coils, which is water cooled. so that you have to tune the magnetic field, fine tune the magnetic field. Otherwise, there will be issue of getting the beam extracted. So you have to have a proper tuning of the magnetic field in a fine tuning. And then, if you go to that is the radio frequency system where the three accelerating Ds are there, and this is the accelerating cavity where you actually get the kick of the ions using the RF field. So these are the Ds, and now if you see, this is the schematic. This is the one, you see the green part is the magnet where these types of cavities. This is the lambda by 2 type, up wavelength cavity, up and down is total about 40 feet. From the median plane, below the ground is almost 20 feet, and above the ground is almost 20 feet. And these similar types of cavities are there. So and in the cavity, this is operating from 9 to 27 megahertz. And you see in the cavity, if you see here, actually the accelerating area, this part is in vacuum. But this cavity, some part of the cavity is in vacuum, some part is in air. So there is a ceramic insulator which is used as an interface between the air and the vacuum. Inside part is vacuum, and now this is the ceramic insulator which is actually used as a RF window, and this is inside part is the vacuum and outside is air. This part is air. So this is the cavity of the, and this is the outer conductor of the cavity. It is and this is basically a outer cavity is the inner conductor is cylindrical, outer conductor is a hexagonal type. Because of a maintenance part point of view, this is not a cylindrical one. So you can take out, if there is any water leakage, etc., you can take out any of the panels and then you maintain the system. So these are the three RF amplifiers. These RF amplifier is the high power amplifier we have made. This is a tetrode based amplifier and tunable depending on the frequency requirement. And this each amplifier is giving power to up to 80 kilowatt at highest frequency, and this amplifier is feeding power to the cavity through, you see, there is a coupling capacitor which is matching the impedance of the cavity, high shunt impedance of the cavity to the 50 ohm impedance of the amplifier output. So this is the, here actually this is the below the ground, here it is connected to the cavity, and then the cavity is this amplifier, there is a coaxial switch, which is, this is the coaxial switch, which is actually either the power will go to the cavity or the power will go to the dummy load. This is a 50 ohm high power dummy load, and if the amplifier is to be tested, we can use the dummy load, and the RF switch has to be connected towards the dummy load. So this facility is there. So immediately, suppose we want to test, within a minute we can change over and use the dummy load to test the cavity. So this is the amplifier we have made using the tetrode. This is the InPAC tetrode we are using, and this is also having the cavity, which is also tunable, but the cavity size is less than the main cavity size, but the structure is almost similar. And this is the input circuit of the cavity we have made, and then because input, this is the grid side, this is the cavity of this amplifier is operating in a class AB mode. This is the input structure. So when we flip the power, there is a distribution of the impedances so that proper symmetry is maintained. So this is the input structure, and the cavity, and it is all interlocks are PNC based, interlocks for the RF system. And this is, as you know, if RF people are here, they can understand that when this cavity was first tuned, whenever it is tuned, we use the network analyzer to tune the 50 ohm system, and then we feed the power to the cavity. So at low power level, we test it. And there is also a closed loop trimmer control system, because fine tuning of the frequency is required. This is a closed loop trimmer control system, and all the trimmers are hydraulically controlled because streamer is very near to the magnet, high field magnet, 5 Tesla. So if there is some leakage, the motor will not, stable motor will not work. So because of that, the hydraulically driven system is there for streamer control and coupler control. And then you see the cavity scientific this measurement of the cavity quality factor that is being done by this cavity time constant method. So probably you may be knowing is the pulsing is done, and then you see the you find out the quality loaded fuel is loaded quality factor, and depending on that. But one point one has to be remembered that this measurement cannot be done during multifacting phases. When everything is stable, then only, because in the multifacting time, the signal is not the right signal like this. The signal is this, so that time, whatever you measure, it is a wrong measurement. So, and D voltage measurement, so what is the voltage in the cavity, and it is basically, so using the non-contact method, this is basically the X-ray Bremsstrahlung method. You can you know that the end point of the X-ray Bremsstrahlung is the highest energy. So we measure this thing using the D voltage measurement using X-ray method. So this is the end point. So in this case, we get the say 40 kV voltage. This is the 40 kV, and in that measurement there are a lot of piled up things. So you have to deduct all these events, whatever pile up is taken place. There is a standard method is there, so you have to do that. And also there is a, as you know, this is a 3D system. The phase stability is the most important. So we have used a point to one plus minus point, because our three cavities are in one plus minus 120 degree apart. So it should be 120 plus minus 0.1. Otherwise beam will be unstable. So these are the assembly I have already shown. So I am not going into the. Now this K500 superconducting cyclotron brings a paradigm shift in nuclear physics research in India. So as you know, this is the K130 cyclotron, Delhi, Mumbai, electron energy. So these up to this. So after that, this part, this is K500 cyclotron, and the Russian and Texas, MSU, etc. And beyond that, up to this is the LAC. So we are operating in this region actually. And this highest energy beam is available only in VCC using this K500 cycle. Now there are various, I am just giving a few examples of the experiments what already done by the users. So using the oxygen 16 beam 363 MeV, using the team target, you see decent distribution of actinides. This is actually 5 to 6 MeV. But the Fisher barrier height is 37 MeV. So K500 superconducting cyclotron allows us to carry out such experiments. So these experiments have been done, and one of the experiments have been done, and the publication is in the process. As you know, this superconducting cyclotron, this was in South Korea. This aspect was News Digest. It was published in 2023. So now I am coming to the radical cyclotron facility. As the accelerator is besides the basic science research, it is also having the applications in medical science. For in our case, this is a radioisotope production. Here, 30 MeV medical cyclotron facility in BCC is in another campus, and it has 5 beam lines. That is one for PEG and 2 for SPEC, and another 2 for R&D for material science research and ADSS time. So this is the PEG isotopes like positron emission tomography. That is main workhorse is the this F18 isotopes, And then another is a staked isotopes, various staked isotopes like gallium-67, gallium-68, like that, helium, iodine, etc. And we also have the radiation damage studies being taken place using this is a 350 microampere machine. So they have already used up to 50 to 100 microampere, but for that to use that array, you have to have your target fully proper. So that whenever the material science people are doing, they have to make their target cooling system so that because it is a power is a very huge. If you go to microampere, huge power. So this is the medical cyclotron. So this one is the paid beam line, and this is one spake, and this is another spake beam line, and behind this there are two beam lines for material science and ADS studies. So this machine is basically a machine working in the about 65 megahertz in 4 harmonic mode, and its magnet weight is 50 ton. And it is a room temperature magnet is 1.7 Tesla, and 50 to 30 MeV it can be extracted. So these are the specifications of the D voltage maximum is 50 kilovolt, and RF power is maximum 40 kilowatt is required. And so now I come to this is the beam sets part is already we have developed those beams and already radioisotope package produced and delivered to the hospitals and regularly being done. And for example, F18, this is the PET isotopes, about 110 minutes half-life, and used for various diagnostic purposes. Copper 64, that is using the nickel 64Pn reaction, and this is basically a theranostic isotope. It is 12.7 hour that is in half-life, and it is also, other than producing positron, it will also produce the beta, so it is used for therapy. And technetium 99, which is from 100 moly P12 reaction, it has been produced. Gallium 68, which is a 68-minute half-life. Basically, very near hospitals it can be given because half-life is very low. So that is regularly being done for this gallium 68 dotatate and PSMA. This is from zinc 68 is the target material, and also other isotopes. These isotopes actually above previous things it is below 18 MeV is enough. Machine below 18 MeV proton beam, but above 18 MeV this for to produce these isotopes you need above 18 MeV. For example, gallium 68 we have produced at around 22 MeV, and gallium 67 and iodine 123 we have done from tellurium 124 PN reaction that is at 28 MeV, and then thallium 201 this is around 28 MeV between 27 to 35. All these isotopes have been already produced, and besides this, BRIC is also in the process of producing a germanium 68 to gallium 68 generator for commercial purposes, because currently this generator is being imported, and so if it is produced, then it can be indigenously supplied to the various hospitals. And this is some pictures of the medical cyclotron. These are the two spake and spake beam lines. This is the PET vault where the MPG is produced from increased to 18. And this is the beam on the beam viewer. And this is the control system from the computer. And these are the material science beam lines. And the ADSS target is going down. And this is the material going to the material science cave. This is the material science cave where the beam lines are coming from here, and then again it branches into two high dose and low dose beam lines. And this is the high dose and low dose beam lines, the closer picture. These are the more closer, high dose and low dose. And these are some material science beam optimization was done, and the target holder was water-cooled target holder was made in our ECC workshop, and then it was utilized. These are the target holders, design, etc. is connected to the system. And this is the ADSS beam line, and it's going down to the under the surface, and this is up to this is the minus 10 meter level in the building. And there are certain, as you see, in the spaced isotope, when it is produced at the this target, and then the target itself, total spaced target itself, after irradiation, it is to go to the hot cell, and in the hot cell, it is going through this, port, and it is going down, and you see this blue line, blue types of where it is there. It is basically sensors are there every 1 meter, so that if somehow the target along with the target, radiated target, is stuck somewhere, then you can get the signal in the computer in the control room, then with proper measure by the health physics, then one can open and see where it is stuck and take out. So that facility is also there. So these are the target stations, various target stations. And this is the paid hot cells, and this is the clean room corridor, and this is the paid hot cells, 2 paid hot cells, and this is the cell 9 staked hot cells. So these are the details of how the production is done, say FDP and all these things. So I am not going into the details of it because time is not there. So using the O18 enriched water, this is being produced. And then after that, this is one of the examples of utilizing the effective NaH, sodium chloride. Bone scanning is done in a hospital. So this is the picture we got from the hospital using our radioisotope. So very nice, clear diagnosis is done, and commercially it is being given to the hospitals. This is the gallium-68 produced, and this is the different purity, etc. 99% purity, RNP, radionuclide purity. And this is the gallium-68 PSMA is done. This is a picture from the hospital we received. One of the hospitals, then gallium-67 produced. Then thallium 2 kilo-1 chloride, this is produced using this P3N reaction. And then there are a lot of, this is the first time in India this is produced, thallium-201, because this happy MAD medical cyclotron is the one medical cyclotron available. So first time here in BCC it has been done, and it is at 28 MAD. These are the various products, this RCP and RNP, radiochemical purity and radionuclide purity. And this is the thallium-201 used in the hospital for a patient. So images of biodistribution. And now, besides medical field, there are also, as I have already mentioned, this material science and experimental nuclear physics, the applications of cyclotron. So for basically basic research purposes, so various beams have been used. In this case, alpha beam has been used, and because BCC is the only place where you can get alpha. And these are the various infrastructure for detection infrastructure at BCC for experiments. So all these facilities are available and being utilized for experiments. And these are various experiments. For example, study of wild state in carbon-12. So for that using this 10.6 MeV proton beam, and then various systematic investigation of the isotopic dependence of nuclear level density that is being done, that is already done using the K130 cyclotron. And so I am just giving a few examples of these experiments. All these experiments have been published in the peer-reviewed journal. So this is, and also the first observation of safe coexistence of this 115SP, and that is also published. So few examples, and in this experiment was actually published in peer. physics review later. So using the K130 beam, this beam, the target was the gold 183. So these are the experiments carried out. Various experiments, the stringent test of alpha decay and the lattice compression using this 29 MeV beam alpha beam. And then study of giant dipole resonance at low temperature, that is also using the beam from cyclotron. So lifetime measurement. So all these experiments have been just going through these. So various. So my point is that I want to emphasize that the basic science research is the main aim. Was the main aim for the cyclotron to be established in India while this Professor Meghna's thought. After that, the utilization of cyclotron was also for medical purposes as well as for industrial purposes. So, for example, here the evaluation study of the structural reactor structural material was carried out, are being carried out, are already carried out, and also being carried out and when requirement comes from the DAE or PRC or APCI. So that is also done. I am not going into the detail of it. So besides this, now I have told that we are also in the process of making a indigenous 18 MeV medical cyclotron, because our 30 MeV medical cyclotron is a IBA medical cyclotron. So now this is the medical cyclotron. The various parts are already, for example, the magnet iron machining is going on in BRC, CDM as well as DCC workshop, because to expedite the things we are making it in both places. So very soon, by August it will be completed. We are expecting the magnet machining and the magnet coil has been already manufactured in Indian industry, and that is already in place. That is already delivered to the BRC CDM, because the first testing will be done at CDM and then we will take it to the DCC and then we will install there. And besides this, RF structures are being, fabrication of the RF components and amplifier is in progress. So various parts already manufactured, and also the ion source have been already tested up to 1.1 milliampere. It's the NTFE based, the permanent magnet based multicast ion source, and also we have already made another samarium carbide based ion source. So 2 ion sources we have made. Also the Faraday cups and other things. For example, we have a physics design. Obviously, it is completed before already. And so this is we are thinking, we are expecting by the end of March 2026, we will be able to test the 18 MeV medical cyclotron beam. So another thing is that we have a proposed proton cyclotron for Umuri facility 50 MeV 200 microampere. That design is already completed and it is published. So thank you very much for your attention.
Thank you, sir, for an insightful and provoking talk on cyclotron technologies. Now I request our dignitaries to take their seat on the dais. If any of the participant is having any question, we can take 1 or 2 questions. If there are no questions, let us move ahead. It's It's now time for the InPAC 2025 Abstract Booklet Release Ceremony. I request the dignitaries on dais to unveil the abstract booklet of InPAC 2025. It's now time to present memento to our esteemed guest as a token of our deep appreciation and sincere gratitude. I request Shri Unmesh T. Malshi, Director RRCAT, to present a memento to our chief guest, Shri K.N. Vyas, former Chairman, Atomic Energy Commission and former Secretary, Department of Atomic Energy. I also request other dignitaries on the dais to join Director RRCAT in presenting memento to our honored guest. Now I request Shri Tushar Kultamekar, Additional Director RRCAT, to present a memento to our guest of honor, Dr. Sumit Soam, Director VCC. Now I request Shri Sanjay Chokse, Chairman, Local Organizing Committee, InPAC 2025, to present vote of thanks.
Thanks. Thank you. It is a privilege and a great joy for me to extend a vote of thanks for all those who have contributed in one way or other to make this function a grand success. Shri K.N. Vyas ji, Chief Guest of today's function, Guest of Honor Dr. Sumit Soam, Director RRCAT, Tushar Kultamekar ji, Additional Director RRCAT, Manoj, Director PMG, distinguished scientists, participant delegates, ladies and gentlemen. First and foremost, I would like to express our deep gratitude to Shri K.N. Vyas ji for accepting our invitation to be the chief guest of today's inaugural function, addressing the gathering and inaugurating InPAC 2025. We are happy to have with you, sir, today, Dr. Sumit Soam, Director VCC, as the guest of honor today. Sir, we are thankful to you for accepting our invitation and be with us and delivering the nice talk. Shri Malshi ji, Director RRCAT, was always with us, giving guidance to all stages for organizing this conference. When we approached for him for organizing the conference, he readily agreed for the same. He has been our driving force behind organizing this conference. We are grateful for all the support rendered for organizing this conference at RRCAT. Thanks to Kultamekar ji and Lard ji, Chairman and Convener of National Organizing Committee, for their suggestions during various stages of organizing this conference. Thanks to Indian Society of Particle Accelerator for accepting the proposal for organizing the conference under their aegis. Thanks to all RRCAT retirees who have accepted our invitation and being with us, especially Gurnam Singh ji, Gopal Joshi ji. Their contribution to build the accelerator will be remembered in this community. And thanks to Dr. Saravanan, convener, and Dr. Vikas Jain, organizing committee at RRCAT. They have dual role of organizing the committee and DISPA. We are thankful to all the invited dignitaries and all the invited speakers who have accepted our invitation and came all along here to deliver the talks. We express our sincere thanks to all participants who have arrived here to present their work during the conference. On behalf of organizing committee, I thank BRNS for funding the conference. We are also thankful to the group directors of RRCAT, ODs and independent section head, lab heads for providing all necessary support for the event. We thank various members of the committee, subcommittee and volunteers who have worked very hard to make this necessary arrangement for making InPAC2025 a success. Sincere thanks are due to various sections of RRCAT, including administration, accounts, security, CISF, the staff of Director Office. Finally, thank you to the organizing committee and volunteers for their hard work and dedications. Your efforts have been ensured a smooth and successful conference. Thank you all for your participating and making this memorable event. A special thanks to the auditorium, construction and service division, horticulture, electrical section, guest house, computer section division for providing timely help in organizing the conference. And special thanks goes to our sponsors and industrial partners for their generous support which made this event possible. I would also like to thank all the industrial exhibitors for putting their stalls and exhibiting their latest product for the benefit of the participants. On behalf of the organizing committee, I give the opportunity to members to the press who have accepted our invitation and coming here for the inaugural function. Finally, I thank one and all for being with us for the inaugural function and participating in InPAC2025. I realize that I missed a few other institutions and individuals who have been supporting us. I wish to be forgiven for not specifically expressing our gratitude. Thank you.
Now I request you all to rise for the national anthem.
जनगणमन जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तब शुभ नामे जागे तब शुभ आशीष मांगे गाहे तब जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय जय हे।
I now invite you all to the inauguration of industrial exhibition. Director RRCAT and other officials shall lead our respected guests to the exhibition site. After the inauguration, all are invited to the high tea at the terrace. With this, we come to the close of this inaugural function. You are requested to assemble back in the auditorium within half an hour for the first technical session of InPAC 2025. Thank you.